Thanks very much, Fergal, and thank you to Brian and to Paul for the invitation to come and speak here. At UCL, we collaborate quite a lot with UCC, and so it's great to have the opportunity to speak to one of the leading energy system modelling teams in Europe and in the world. So, what I'm going to speak about is a paper which myself and my colleague, Professor Paul Ekins, published in Nature at the beginning of this year, looking at this idea of what fossil fuels have to stay in the ground if we're going to take climate change seriously. And Fergus unfortunately stolen my key findings, but hopefully there'll be interesting things to say as we go through. So, but before looking at the Nature paper itself and what all of this means, because this is mainly a modelling exercise, I think it's worth just dwelling very, very shortly on some of the modelling aspects and what it means to try and model these sorts of things. It's important to acknowledge that when you're trying to model the global energy system out to 2050, that you're going to get it wrong. And that's mainly because it's incredibly complex and you're looking out over such a long period of time. We've heard the uncertainty over fossil fuel prices already, and that's obviously one of the key aspects, but there's so many other complexities within the energy system itself. And then when you add in the complexities that there are because of the climate system, things can get very difficult. But at the same time, we in UCL, and I'm sure my UCC colleagues would agree, that it's important to try and model these things, because the alternative is really just to rely upon people's opinions or ideas which aren't quite so easily tested. And at least with models, you can always test the assumptions and look at what the results are sensitive to, and look at what changing some of the key inputs can mean for the results. So to have any faith in what models do and the results that they give, there's three really key aspects to the model itself, and Brian mentioned one of these already. The first of these is the robustness of the structure, the modelling framework. And for this paper and for the study which we'll be talking about, we use this times modelling framework, and the global version of this was called TIAM, and we have a version in UCL called TIAM UCL, which has a number of changes from the version we have here. And as Brian mentioned, this is used by a huge number of different universities and organisations across the world. It's been developed over about 15 or 20 years. And so there's a lot of thought and time and effort gone into this framework, which hopefully gives a bit of confidence that the framework is robust. The second thing which needs to be, you need to have faith in results, is the plausibility of the input assumptions. So within TIAM UCL, there's around about 10,000 different technologies, some of which I'll discuss shortly. And for each of these, you have to specify things like what are the costs of them, when do they become available. And this really feeds into the third aspect, which is the quality of the data which goes into the model. These sorts of models are often described as garbage in, garbage out, but we try pretty hard and spend an awful lot of time trying to ensure that they're not garbage in. We really want to try and make the input assumptions to the model as robust as possible. But at the same time, we're always willing to update these assumptions. What the cost of solar is going to be in 2050 is more or less unknowable, but as new information becomes available, we update or we improve the assumptions within the model so that we can have some faith of what the model is saying. And as part of the peer review process for Nature, all three of these aspects were tested and were reviewed in some way. So hopefully that gives a little bit of confidence that the results are grounded in reality. But to speak a little bit more about the model itself, TIAM UCL, there are 16 regions within TIAM UCL, which are shown in the map there at the top right-hand side. This model was developed over the past 6 or 7 years under a grant from the UK Energy Research Centre, and because it's funded by the UK, one of their requirements was that the UK is one of the regions within the model, which is why it's broken out from the European region there. It's not particularly interesting for the basis of this study, but it means that there are 16 regions in our version versus some of the other versions of TIAM out there, which have a small number of regions. And the second aspect of TIAM is that it's a technology-rich model. I mentioned there's around about 10,000 different technologies within the model. And within each of these are specified within each of the different 16 regions. And we specify things like capital and operating costs, the efficiencies of the technologies, how these efficiencies and costs change over time, when they first become available, and so on and so on. And within each of these 16 regions, the way the model starts is by you specify the energy service demands within each of these, and you project the energy service demands from now out to the long term, which in this case is out to 2100. And energy service demands are things like how much are people going to want to heat their buildings in the future, how far are they going to want to drive, what industrial activity, how many tons of steel are you going to produce. All of these different aspects are assumptions, input assumptions within each of these 16 regions. And the way the model operates is that it finds the cheapest way of satisfying all of these energy service demands, given the primary energy sources which are available to it, and given the technologies that are available to it. And the schematic on the bottom right there tries to demonstrate this. So along the bottom in red there we have these energy service sectors. So you have the agricultural, the residential, the commercial, transport and industrial sectors. You have energy service demands within each of these sectors within each of the 16 regions. And then the top line there in blue, which probably hasn't come out at all, is the fossil fuels. So you have the traditional sources of meeting these service demands. And then in the middle you have the more renewable sources, bioenergy and nuclear included. And then down the side there we have the climate model, and this is one of the different aspects from when you model in a global context is different from the Irish context or the UK context. Is that you can see from combusting and using fossil fuels what effect this has upon emissions, CO2, methane and N2O emissions. Then what happens to the atmospheric concentration of these gases. As you combust more, the atmospheric concentrations will go up, and then that will give you a temperature rise over the long term. And so you can use this climate module in a number of different ways. First of all, you can just say, well, if we want to find the cheapest possible way of satisfying all of these energy service demands, what is the temperature rise going to be? Alternatively, you can use this climate module to say, to cap at a certain temperature rise, and we'll be discussing the 2 degrees temperature rise. So within most of these scenarios, what we do is we use the climate module to say, you have to satisfy all these energy service demands in the cheapest possible way, but also ensure that the greenhouse gas emissions which result from using fossil fuels aren't so great that the 2 degrees temperature threshold is exceeded. But because the climate system is quite complicated and there's a lot of feedbacks in there, you can only get a percentage or a probability chance of a given temperature rise. So the way that the climate module is calibrated is that there's a 60% chance of staying below the given temperature rise. So whenever I talk about the 2 degrees scenario here, this is a 2 degree scenario with a 60% probability. And you can all form opinions as to whether you think that in itself is too high a probability. If governments have agreed to stay below 2 degrees, is a 60% chance of staying below 2 degrees really tight enough? Some people say we should go 50%, some people say we should go for 80% chance of staying below 2 degrees. But the tighter, or the probability that you want to stay below the temperature rise, the harder it is to reach that, and the more constrained emissions have to be. So obviously, whenever we're talking about fossil fuels and what fossil fuels we can use and what we can't use, one of the key assumptions is, well, what sorts and what volumes of fossil fuels exist in the model and in the world that are available to be used. And this is something we spent quite a lot of time working over the past few years, is trying to characterize the fossil fuel resource base within all these 16 regions. So because one of the key definitions and things which are often confused is the difference between fossil fuel reserves and fossil fuel resources. So to avoid any confusion in that aspect, when I talk about fossil fuel reserves, these are volumes of oil, gas and coal which are currently extractable under given technologies and currently extractable given the current economic regime that we're in. And also to be classified as a reserve, there has to be a specific probability of this volume actually being produced in the future. So when we talk about a fossil fuel reserve, this is really a volume which people anticipate or expect to be produced in the future under the current situation. The fossil fuel reserves is a small subset of the much wider resource base, which are volumes which potentially aren't currently extractable given technology. So future technology advances might mean we can extract more oil, gas or coal in the future. And also they're volumes which aren't necessarily economically extractable currently. So because the oil price, for example, has come down, you would expect that some volumes of oil which we thought were economic to extract last year now aren't economic to extract. And those are fossil fuel resources versus the reserves, which is a much smaller subset. And what I show here is the supply cost curves for oil in the top left, gas in the top right, and coal at the bottom, separated out by different types of fields and different types of oil and gas and coal which exist in the world. So hopefully you can read the text there. So for example, you have fossil fuel, or you have oil reserves in fields that are currently producing or are scheduled to come online very shortly. And so, as you'd expect, these are ones which are most economic and so are therefore generally focused towards the bottom left of the supply cost curve. So they're the cheapest sources which we can get. But then you expect to discover some more sources in the future, so that's your resource base, so they're also included there. And then you also have things like the unconventional sources of production. The Canadian oil sands is often discussed. Venezuela has its own unconventional sources of production called the extra heavy oil. And also, separate from the shale revolution, you also have, which has been examined in a lot of detail in the US in the past, but never actually got any commercial production, it's called oil shale or kerogen. Very different from the hydraulically fractured fossil fuel sources. Oil shale is very different, but it's a potential source of oil, so it's included on these supply cost curves. And gas, you have all the conventional sources as well as the unconventional sources, such as shale gas, such as coal bed methane and tight gas. So moving on to the paper itself and the research question, the climate studies which have been coming out over the past 5 or 6 years have shown that there's a pretty close relationship between the cumulative amount of emissions that occur over a given time frame and the expected level of climate change, the expected amount of global warming that we can expect in the future. And this has given rise to this idea that there's a certain carbon budget, a certain cumulative level of emissions which we can afford to emit for a given probability of staying below a certain temperature rise. And people have seen this, taken this idea and put that together with the political agreement that the temperature rise shouldn't exceed 2 degrees. And so you get basically what they call a carbon budget, which is around about 1,100 gigatons, billion tons of carbon, which can be emitted between 2011 and 2050 if you want to have a reasonable chance of staying below 2 degrees. And when you compare this number to the amount of carbon and the amount of greenhouse gases which would be emitted from burning all of the fossil fuel reserves and resources that we saw before, people have noted that actually just within the smaller reserve base, the embodied carbon within those volumes of fossil fuel already exceed this carbon budget by around 3 times. And what people have noted in the past is that therefore means you can only afford to burn a third of the oil, gas and coal reserves that there are available around the world if you want to have this reasonable chance of staying below 2 degrees. And that's a very interesting number, and people did an awful lot of work with that in the past to raise awareness of this issue. But what we wanted to do was to use TAM-UCL, to use a model which has a much richer and more dynamic representation of fossil fuels and the use of fossil fuels to say which of the oil, gas and coal do we want to use. All of the fossil fuels aren't created equal. Gas is a lot cleaner than coal, and oil is much more useful than gas and coal, given that you can use it in the transport sector. So if you want to reach 2 degrees in a cost optimal way, in the cheapest possible way, and everyone works together towards reaching 2 degrees, which of the oil, gas and coal do you use, and whereabouts is that located? And so that's really the key aspect, the key question that we wanted to answer as part of this paper. But I mentioned that before we get on to the headline results from the study, I mentioned that the energy system is a pretty complicated thing to examine, especially when you're looking at over the time frame of 2050. And to demonstrate just one of the key uncertainties, one of the big uncertainties that exist, when you look at in the past at how the energy system of the world has developed and matured over time, there's been a pretty close relationship between the amount of energy that we use and GDP growth. So in the future, you might expect that if GDP growth increases, that energy use is also likely to increase. But there's a pretty uncertain range in what's going to happen to GDP looking out over the future. So on the graph on the left-hand side there, we have the range of anticipated or expected GDP growth on a global basis between 2010 and 2050. And these are all of the scenarios that we used within the IPCC study of last year. So these are all plausible projections of what might happen to GDP over the next 40 years. And we can see that in 2050 there's around about 100% range of uncertainty there in what global GDP might actually be. And this range, this uncertainty range, given the historical relationship, you would anticipate would mean that there's going to be a pretty broad range in the amount of energy and the amount of fossil fuels that we're going to use in the future. So one of the first things that we did as part of the study was to look at some of these major sources of uncertainty in how much fossil fuel and in the energy types that we use, and look at what does this mean for cumulative production of the fossil fuels, and that's what's shown on the right hand side there. That has the bars show the cumulative amount of oil, cumulative amount of gas, and cumulative amount of coal which are used between 2010 and 2050 on the different scenarios which are run. All of the small bars are ones which stay below 2 degrees. There's 60% chance of staying below 2 degrees, and the two on the right is the one on the farthest right is a 5-degree scenario, because this is a temperature scenario which reaches around 5 degrees in 2100, and then one which stays at about 3 degrees by 2100. And all of the different bars show different sources of uncertainty which we've examined under these different scenarios. So the one on the left-hand side is the core, the central 2-degree scenario. But then we looked at things like what happens if fossil fuel costs are much higher or much lower, which are the second two bars. What happens if the availability of bioenergy is much higher or much lower than the central scenario? If oil availability and gas availability is much higher or much lower, and then things like demand, which are labelled there dem high and dem high. If GDP is at the lower end of this range or at the top end of this range, and population similarly, and look at the impact, what the influence do all of these major sources of uncertainty have upon the cumulative levels of fossil fuel that we use in the future. And what we can really see here is that while these major sources of uncertainty are big and will have major influences, whenever you actually want to stay below 2 degrees, they're not as important as you might anticipate. There isn't actually a huge amount of variation between a lot of these bars as you go through these major sources of uncertainty. The y-axis there is in zettajoules, which is 10 to the 25 joules, but effectively the world uses 0.5 zettajoules currently total energy every year. So it's quite a large unit of energy, and you can see that the really big difference is between those small bars that stay below 2 degrees and the 3 and the 5 degrees ones. So just to reiterate, although there are an awful lot of uncertainties in the energy system, if you want to stay below 2 degrees, a lot of these uncertainties don't have as big an influence as you might anticipate. So coming onto the headline results now from the study, we've heard already that on a global level, 80% of coal reserves, 50% of gas reserves, and a third of oil reserves should stay in the ground if we want to have a reasonable chance of staying below 2 degrees. And the way these numbers were generated was by comparing the cumulative levels of consumption on a global level or on a regional level with the amount of reserves which are estimated to exist within each of these regions or on a global basis. But going one level further and looking at more at the regional level, we can see there's a real disparity between what happens in some regions compared to this just looking at the overall headline figure. So if we look at coal to begin with, for example, you can see that the United States, which has absolutely huge volumes of coal reserves, the former Soviet Union, which is predominantly Russia for coal, and OECD Pacific, which is predominantly Australia in this case, have to leave well over 90% of their coal reserves in the ground, meaning they can use around or less than 10% of their coal reserves if we're having this global effort towards 2 degrees. Looking at oil, again, there's slightly less difference between some regions and others, apart from Canada, which you can see has a far greater level of its oil reserves which need to stay in the ground, and we'll come back to the reason for that shortly. But we can also see that in absolute volumes, the Middle East, for example, has to leave an absolutely huge amount of oil in the ground. 260 billion barrels of oil is, broadly speaking, equivalent to the current reserves of Saudi Arabia. So under this 2 degree scenario, what this analysis is suggesting is that the Middle East has to effectively leave all of Saudi Arabian oil in the ground. Obviously, it's not just Saudi Arabian oil would have to take the hit in that case, but it has to leave the equivalent of all of Saudi Arabia's oil in the ground. That's obviously going to have a huge impact on the development of the Middle East and how they develop their reserves in the future. On gas, the Middle East also takes a very large hit, as it were, under this scenario. So we can see that of the global total, 95 trillion cubic meters of gas which has to stay in the ground, the Middle East holds over half of this level of gas. And again, if one region is having to take a very large hit on its reserves, there are questions to be asked in both a policy and market perspective on how is this going to come about, and how might these regions be compensated for having to sacrifice a large proportion of their fossil fuel base. One thing which we didn't include in the paper, but which we were asked about in quite a number of times subsequently, was what's the difference between this 2-degree scenario and one which is a bit more like a business as usual scenario, looking out into the future. We try to avoid phrases such as business as usual because it carries with it a lot of connotations as to what current policies are doing and so on and so forth. So what I have here is this 2-degree scenario and a 5-degree scenario. 5 degrees is where we just abandon any efforts to reduce carbon emissions in the future. So the black line is the 5-degree scenario and the green is the 2-degree scenario. And looking at coal, you can see there's a massive disparity between what happens for coal production globally between these two scenarios. So broadly speaking, it continues to increase out to 2050 in the 5-degree scenario, whereas in the 2-degree scenario it really just drops off a cliff. And the cumulative difference between those two scenarios for coal is around about 290 billion tons of coal, which difference between these two. And there's around about 1,000 gigatons of coal reserves, so that's around about 30% of coal reserves different between the 5 degrees and the 2-degree scenario. And there's also quite a big disparity we can see with oil. So in the 5-degree scenario, again, we can see this rapid increase out into the future, whereas in 2 degrees it more bums along at current levels. And the difference between those is around about 220 billion barrels of oil. So again, that's on an order of magnitude similar to what Saudi Arabia holds in its current oil reserves. The gas picture is quite an interesting one. It's very, very different from the other two, particularly because we can see that in the short to medium term, out to about 2035, gas consumption or gas production in the 2-degree scenario is higher than in the 5-degree scenario. And what's happening there is because you have this very, very rapid reduction in coal consumption or coal production, the shortest term and the cheapest thing and the most available thing that you can do is switch from coal to gas to reduce your emissions very quickly. And that means that actually you get a much more rapid increase in gas consumption in the 2-degree scenario compared to the 5-degree scenario up to a certain point. So this analysis would just suggest that up to around 2035, gas is greater in the 2-degree scenario than the 5-degree scenario, and this is playing along with this idea that gas can help as a transition fuel or a bridging fuel out to a low carbon future. There's 3 more specific aspects which we can use which we can use TMUCL to look at, and which I'll run through relatively briefly. So the first is carbon capture and storage. So in the core 2-degree scenario, we allow carbon capture and storage to be deployed. It can first be deployed in 2025, which we've been criticised both that it's far too optimistic, given that there's very few plants, and also that it's far too pessimistic, given that there are some plants. And so 2025 seems, broadly speaking, to us, given that we got criticised by everybody, a reasonable middle point as to when CCS might become available in the future. So CCS is available in that core 2-degree scenario, and what a number of companies and politicians have been saying is that, well, if we can get CCS right, we can produce all of our fossil fuel reserves that exist. So we wanted to test that assumption by comparing the production in this core 2-degree scenario with one where you don't allow CCS to be developed or deployed on any industrial or electrical process in the future. And so the table there shows a difference between these two scenarios. So the top one there is the volumes that we saw previously on a global level. So again, 82% of coal, half of gas and a third of oil. And in the lower row is what happens if we don't allow carbon capture and storage. And we can see that there is a difference between these two, but that difference isn't really as great as might have been expected. So there's around a 6 percentage point increase in the amount of coal reserves that are produced. That's a lot of coal, but it's certainly not saying you can develop as much as is available. And the difference with oil and for gas is much smaller. So it's only around about a 2 percentage point increase in the amount of oil and gas reserves that you can produce under the 2-degree scenario if you have carbon capture. And there's a number of reasons for that which are listed there. Why this effect is an awful lot smaller than potentially people are hoping, and certainly how they've been talking about carbon capture. The first is that because you can only have it available in 2025, and because all technologies take a while to mature and for the market to be developed, means that there's only a certain rate at which this technology can be deployed and rolled out and looking out into the future. And that means that whenever you're looking at the 2010 to 2050 timescale, actually carbon capture is a little bit of less of an effect than you might expect. Simply because you can't deploy it on every single power plant or every single industrial process that you might want to. And the two other aspects are that carbon capture is, as we assume, is going to be quite expensive. All the estimates are that it is going to be very expensive. And so even if it is available, the model doesn't necessarily choose it. Another very important aspect for carbon capture is that it can't capture everything. Coal is an incredibly dirty fuel, and even if you capture 90% of it, which is broadly speaking what we assume carbon capture can do, that 10% of emissions becomes incredibly important whenever you want to have a completely decarbonised electricity system. Brian mentioned before the importance of decarbonising the electricity system quickly and rapidly so that you can then use that carbon neutral or potentially carbon negative electricity to decarbonise other sectors. If you want to decarbonise transport, you might be able to use electricity or residential heating, for example. But you need carbon neutral electricity to help that decarbonisation process. And if you have something which is still giving you a small but non-negligible amount of carbon emissions, such as coal CCS, that means that actually you might not want to do it, and the model actually those residual emissions become increasingly expensive as you move towards 2 degrees. So it doesn't really get deployed quite as much as might have been expected. Another aspect which you can look at with TAM-UCL is that not only do we have this regional definitions and characterization of the fossil fuel resource base, but we also include within that the Arctic resources. There is anticipated to be huge volumes of oil and gas in the Arctic regions, which a number of companies are actively looking for. And we're able to compare what happens to the development of these Arctic resources under a 5-degree scenario with a 2-degree scenario. And Arctic oil is developed if you decide that you don't particularly care about mitigating carbon emissions, but none of it is developed or produced if you do care about it under the 2-degree scenario. And the headline conclusion from that for us was that really you should classify Arctic resources as unburnable. They're not required if you want to have a reasonable chance of staying below 2 degrees. I mentioned Canada previously, and that it has these absolutely vast volumes of unconventional oil, the oil sands or the tar sands, depending on your perspective. And you can compare how the development of these oil sands differ under different temperature scenarios, which is what's shown on the left-hand side there. This is the bitumen production, the total levels of production of these oil sands using in situ processes. In situ processes are where you effectively dig into the ground and then pump down a load of steam and heat to melt the oil so that it will flow to the ground more easily. And this is used in Canada currently, and it produces around about 1 million barrels per day. And we also have mining processes which are very different, but we just got in situ processes here. And you can see under the 2-degree scenario that you do get continued development, production of the oil, some of the oil sand reserves out to 2050. It does, but saying that, it does drop from current levels. This is very different from what the Albertan regulators and the companies out in working in oil sands are projected is going to happen to oil sands development over the next 20 to 30 years. But even saying that, even that you don't have this increase in the 2-degree scenario, this is only possible to continue current levels of production if you decarbonise the energy inputs which are required for that heat which has to go into the ground. So on the right-hand side there show the sources of the carbon intensity and the sources of heat which for this melting of the oil. So currently gas is very cheap in Canada, and they use this cheap gas to produce steam, pump that steam down the ground, and you can see that's the main yellow bar there. And this means that the oil sands are one of the most highly carbon intensive sources of oil that there are around the world. So for every barrel of oil you produce, it requires about 100 kilograms produces around about 100 kilograms of CO2 for every barrel that you produce, compared to And so that's more or less increasing the combustion amount emissions from a barrel of oil by around about 25%. So it's certainly not completely the highest source of or most carbon intensive source of oil there is, but it's very much at the top of that curve. But the model TAM allows you to switch the sources that are used to produce that heat. So we can see there that over time, after 2020, there's a very rapid reduction in the carbon intensity of that heat. So the model shifts away from using gas, initially using bioenergy in the 2020s, and then using bioenergy with carbon capture to give you net negative emissions for that heat generation. And it's only if this is allowed to happen can you have this level of production of oil sands going out into the future. So not only is the levels of production that the model is suggesting, which are commensurate with 2 degrees, much lower than what people are currently projecting, but even to have that level of production, you have to completely decarbonize your energy inputs. So coming on to some of the findings and the conclusions of what all of this means, one of the first things to understand and to realize is the real disparity that exists between what politicians say and what they're actually doing in the real world. So every country, pretty much every country, is either signing up to 2 degrees or to 1.5 degrees temperature rise in the future. And they go to the climate change conferences such as there will be at the end of this year, and as there have been for a number of years, and they all continue to sign up to 2 degrees. Yet as soon as they get back home and they discover a new source of oil, gas and coal, they think this is great, let's develop as quickly as possible. Fossil fuels are great. We always want to develop all of our indigenous sources as quickly and rapidly and as completely as possible. In the UK, for example, there was a recent review done on how to maximize the economic recovery of North Sea oil and gas. This is what this report would suggest, is that is completely inconsistent with keeping the temperature rise below 2 degrees. Every country will say, potentially, oh, well, we can use our bits of oil and gas and coal. It just someone else has to take the hit. Well, not every country can say that, and at some point, someone's going to have to bite the bullet and leave some of this stuff in the ground. So, for example, what does this mean for what politicians will actually do? Will they slow down their licensing of new oil and gas fields? That might be an optimistic assumption, but these are sorts of considerations which need to be if people actually want to be serious about tackling climate change in the future. And then for the companies themselves which are doing this exploration and development and production of the fossil fuels, what does this mean? Well, companies spent before the pretty dramatic reduction in oil prices, which we have seen over the past year or so. They were spending around about $670 billion every year searching for and developing new sources of oil and gas and coal. That's money which potentially is completely money down the drain, because if you want to stay below 2 degrees, you're not going to be able to continue to bring on new sources of production over and over again. So investors in those companies should begin to question whether really this is the best use of corporate assets. If the companies are pouring money into something which can into reserves which can never actually be produced, there are other ways in which they could use this money, either return it to their shareholders as dividends or whatever, or put it into alternative sources of energy, potentially low carbon sources of energy, to hedge against the impact that climate change might have upon the portfolios of the companies. And as we're seeing with a number of movements around the world and a number of different organizations, it might actually be seen that these companies are too risky, that the divestment campaign which there has been has to date focused predominantly on the moral side of whether it is right to invest in fossil fuel companies. But what this analysis would suggest is that looking out over the medium to long term is potentially a big financial hook, which could give you justification for divesting from these fossil fuel companies if they can't produce an awful lot of their fossil fuel reserves in the future, and if also those fossil fuels will be worth an awful lot less in the future. Lower demand is likely to have an impact upon prices. Are those companies really worth as much as people are currently anticipating in the market? So there could be an economic or financial incentive for divestment from the companies. So just to conclude, and I'm looking forward to the questions, and I'll put the implications back up there before after this slide. There is we think, and hopefully this analysis has shown that the modelling tools can be incredibly useful for analysing potential energy futures, looking out over the long term in a global context. But given that there are numerous uncertainties that exist, it's important to acknowledge that these uncertainties are there and to examine a wide range of different scenarios and sensitivities. But one of the key uncertainties, which we saw from the graph previously, is what's going to happen over climate change. Are people going to properly commit to staying below 2 degrees? Because this is likely to have the biggest impact on fossil fuel reserves and resources that can be used out into the future. And if we want to stay below 2 degrees, very large proportions of the oil, gas and coal, which people anticipate and expect to be produced in the future, are going to have to be classified or should be classified as unburnable. And as we move towards the Paris conference at the end of this year, where hopefully they will thrash out an agreement as to how this will actually be achieved, there's a huge amount at stake, and hopefully this sort of analysis can feed into that process as to who is going to have to sacrifice and potentially lose out as a result of climate change. Thanks very much.